welcome back. We continue from where we stopped. Now still on real analysis, and we are looking at ordered field. Now looking at ordered field, let's look at the following definition for an ordered field. Now a field F should be considered to be an ordered field. Like let's consider a field F to be an ordered field. Now, and let's consider also there is a subset in this ordered field F, which we will term as what P. Since there is a subset P in F, it must have the following properties that we shall list. Now, A, which is what? If there is two elements A and B in our field, in our subset, then there must also be the addition of these two elements in the field. Now, the second one is if there are two elements A and B, which is in the subset, then there must also be an element such that it is the product of A and B, which is also in the subset of the field. And then for C, if there exists an element A in P, which is our field, then one of the following must hold. One of the following must hold. It is either A belongs to P, yes, or A is a special element 0, or there is a negative element A which is in our subset. One must hold, not every, but one of these three must be the actual existence of A in the field, in the subset of the field. So let's move on. Let's go to ordering relations. So looking at ordering relations, we just want to look at some properties, like 4 of them, which is actually the conditions, the situation of two elements or 3 elements in another field. Now let F be another field. Then we have to consider one of the following. It must be that either A is less than B, that is the element A is less than B. Take for example 1 is less than 2. If and only if 2 minus 1 is also in what? In our subset, which is our ordered field. So you can see that that situation must hold. If that situation must hold, then there must also be a situation where A must be less than or equals to B. And what does this mean? This means that is either A is less than B or A is equals to B. That is their values. Is either A is less than B, the first element is less than the second element, or the first element is equals to the second element. So 2 can be equals to 2, or we have a situation we have 1 is less than 2, which is in the subset. And then for the third one, we can have a situation where A is greater than B. And this will imply that our A minus B is also in the subset. And it will not give us a negative element. And the fourth one was consider a situation where A is either greater than B or equals to B. And this can only happen when A is more than B or A is equals to B. So moving on, it takes us to positive and negative elements, because you see in the properties there, we considered a situation where we have B minus A minus B, where they will give you a positive element. So let's look at that. Now an element A in F is called a positive element, or it is called positive if that element is in a subset. And an element A in F is negative if minus A is in P, that if you have a negative element in P. And we should note that any element A is positive if A is greater than 0. So let's look at properties of an ordered field. So the first one we need to look at is our trichotomy law. And what is a trichotomy law? When A is greater than B, or B is greater than A, or A is equals to B, that is, there must be a situation where it is either one of these three we hold. Either A is greater than B, or B is greater than A, or A is equals to B. These are the 3 conditions that must be for the elements. And for our transitive law, if A is greater than B and B is greater than C, then it automatically means A is greater than C. For our addition and ordering, we have A is greater than B and C is greater or equals to D. That means that addition of 2 greater elements is also greater than the addition of the 2 lesser elements. Now for our multiplication, A is greater than B is greater than 0, and then for C is greater than or equals to D is greater than 0. That means A times C is greater than B times D. Since A is greater than B and C is either greater than or equals to D. Now for our squares. Now when you consider an element in the field A, you must have a situation where the square of that element must be greater than or equals to 0. And the only situation where you can have that element to be equals to 0 is if A itself is 0. That is 0 squared will give you 0. If not that, then that element must be greater than 0. So let's move into the next one. Let's move into what we have. So we have our reciprocal. Now the reciprocal is telling us that if A is greater than 0, then the reciprocal of A must also be greater than 0. And then if A is greater than B, is also greater than 0, then 1 over A is less than 1 over B. Now when you check this example, considering our A is 3, considering our B is 2, we see that 1 over 3 is less than 1 over 2. See, the denominator is more heavier. That means 1 over A is less than 1 over B. So let's consider the identity element 1. So if 1 is in F, this means that the addition of this 1 plus 1 is also in F, or at which 1 plus 1 gives us 2. Also 2 plus 1 will also exist in our field, and then we know that 2 plus 1 is 3, and also 3 plus 1 exists also in the field, for where 3 plus 1 is 4. So what this tells us is that as we undergo the addition of our elements in the field, we notice that we'll get greater element than the first, in such a way that now 0 is less than 1, 1 is less than 2, 2 is less than 3, in the increasing order until you get to the limit, until you get to n. Now let's look at the completeness property. The completeness property. And under this we are looking at upper bounds and lower bounds. So let's start. So let F be another field and S be a non-empty subset of F. Now an element P in F is considered to be an upper bound for S. If we have a situation where our S, that is our element S, is less than or equals to P, that is, we consider it to be an upper bound for a situation where that upper bound must be greater than any other element or equals to any other element in the set F. Now, for any set, and which in here we are considering the set to be S, the element S is considered as small s, that is, we consider the small s to be an element in our big S. So our big S is representing our set. Now, like I said, it means that B is greater than or equals to any element in S and an element C in F is also called the least upper bound. Now, when we have an element C to be considered the least upper bound, this means that it must actually be an element that is an upper bound, but it is the least upper bound. Hope you get. Now, C is an upper bound for S for condition 1, and then for condition 2, for any upper bound B for S, C must be less than or equals to B. Now this is a situation where C is the least upper bound, so the other upper bounds must be greater than C in that set. So that's why we have C is less than or equals to B. Now let's also consider a situation where we have a lower bound. Now using an element A. Now an element A is called lower bound for S, for our set S. If A is less than or equals to S for all S that is in S. Now this implies that our A, which is our lower bound, must be less than the elements in S, must be less than or equals to the element in S. An example will be treated for more understanding. And an element D in F is also called the greatest lower bound, which is considered as an infimum too. When we talk about infimum, we refer it to as the greatest lower bound for S. If one D is a lower bound in itself, it is lower bound for S. So, and in the second condition, you must have a situation where our A, our element A, which is a lower bound, must be less than. Let's look at examples on this. Now, for an example, we have the set S. Now, our set S is considered as the closed interval 0, 1. Now, in this S, since it's a closed interval, it means that 0 and 1 is our infimum and supremum. And then since 0, 1 is our infimum and supremum, they are also present. Both 0 and 1 are also present in the set S, since it is a closed interval. So this is a situation where S, the element S is equal to our infimum A, and our element S is equal to our supremum D, supremum C, sorry. So A and C are present in our set. But for the second example where we have open interval 0, 1, you see that there's an infimum 0 and there's an supremum 1, but 0 and 1 are not members of the set because it's an open interval. So infimum A and supremum C are not members of the set S. And also the third example here, we have our set E2 giving us 1 over n such that n is in the set of natural numbers. This also has 0 and 1 as our infimum and supremum, but 0 is not a member because 1 over 0 is undefined, but 1 is a member because 1 divided by 1 is 1. So this, I think that is it. Thus, we can define what array numbers are in this situation. So, defining array numbers now has to do with the completeness property we have been on for quite a few minutes. And then the summary of this completeness property is an axiom. And this axiom is that for every set, that is for every non-empty set, that is the set must contain a member, even if it is a special vector 0. So for every non-empty set or subset S, which is in our field F, and it has an upper bound in F, must also have a least upper bound in F. Now what does this imply? This implies that for a situation where we have a non-empty subset S that has an upper bound, automatically it means it also has a least upper bound. So for this definition, we now have our real number property. So any other field that we have that satisfies this least upper bound action, that it has an upper bound and it has a least upper bound, is now called a real number system. So next, in our next chapter, we look at bounds of real numbers. So in these bounds of real numbers, we were talking about if a subset is bounded below or bounded above, or a situation where a subset is bounded both from below and above. So let's take a short break. We'll be right back to continue that.